Today we're going to do experiment number 30 from Chemistry with Vernier lab book. This experiment is the rate law determination of the crystal violet reaction. It actually involves an investigation of the kinetics of the reaction between 2.5 times 10 to the minus fifth molar crystal violet solution and, in this case, 10 mLs of 0.1 molar sodium hydroxide. As that reaction proceeds, there's a change in the violet reaction that we're going to monitor using a LabQuest and the svis5 spectrometer. The reaction can be done equally well or monitored equally well with a Vernier spectrometer, one of the Ocean Optics powered or Ocean Optics spectrometers. It can also be done with the Vernier colorimeter. To start things out here, the first thing I'm going to do is I'm going to go ahead and connect the svis, which is has a USB output. I'm going to go ahead and connect that to the USB port on the LabQuest. I already have LabQuest turned on, and as I look at the screen there, as soon as I connected that, you can see that the svis has been identified by this red meter that's appeared that indicates that absorbance is being measured on the USB port. The first step I'm going to do is I'm just going to calibrate this just like you do any spectrophotometer. So I'm going to take a blank cuvette. I'm going to place it into the cuvette slot of the spectrometer. Then I tap on the Sensors menu and I choose Calibrate USB Spectrometer. That actually briefly turned off the spectrometer light source, and it did a 0% transmittance calibration across the entire spectrum of 400 nanometers to 725 nanometers. Now the lights turn back on, and as the screen indicates that it's waiting 60 seconds, we're now down to 30-some seconds for it to warm up. The warm-up's important, so we'll go ahead and wait. So now we just have a few more seconds, and we're done. So we'll just tap on the button, Finish Calibration, and then we'll tap OK. And the calibration's complete. Next, we're going to determine the wavelength spectrum for crystal violet solution in order to know what wavelength to use in the experiment. This is where the svis gives us an advantage over doing this with some traditional method like a spectrophotometer or a colorimeter, where typically the student is told what wavelength to use. In this case, they get to discover for themselves what wavelength to use. So what I'm going to do is just place a sample of 2.5 times 10 to the minus fifth molar crystal violet solution into the cuvette slot. Notice on the LabQuest app screen that the mode is already full spectrum, so it's ready to go. So all I really have to do is tap on the Collect button. And when I do that, in less than a second, I get a full spectrum. I'm going to now tap on Stop. And when I do, it auto-scales, and also notice that it selects the peak wavelength. And if I track that down to the wavelength x-axis, down in the lower right-hand part of the screen, I can see that it's selected a wavelength of 585 nanometers to use for the remainder of the experiment. And LabQuest can remember that wavelength for the next steps. This is also a teachable moment for the student in that if he or she looks down at the violet region of the spectrum down towards 400 nanometers, they can see that the absorbance is actually very, very close to zero. And this would not be a good wavelength to use because, in this case, it's a violet solution because most of the violet light is being transmitted. They can also see then that the absorbance that they want to use is somewhere else in the spectrum, in this case towards the yellow end of the spectrum, or around 585 nanometers. Next, we're going to change the mode that we use. Currently we're in full spectrum mode to time-based data collection. To do that, I'm going to tap on the Meter tab to return to the meter. Over to the right, you can see mode is full spectrum. I'm going to tap on mode to change it. I'm going to pull down menu just to the right of the full spectrum, and I'm going to choose time-based. Notice when I do that, I'm provided with some default values. The rate is 1 sample per second, the length is 200 seconds, and those values are just fine. So now I'm going to accept those by tapping on OK. And it asks me, do I want to save that unsaved data, that's the spectrum, and I'm going to choose not to. There's no reason to do that, so I'm going to discard that. And now I'm back to the main screen, and notice that now it says I'm going to measure absorbance at 585 nanometers, and it's accepted my values. Next I'm going to start the reaction between crystal violet and sodium hydroxide. So I've got 10 mLs of both of those solutions, and I'm going to pour those alternately into a 100 ml beaker. And without wasting any time, I'm going to stir those to make sure that's homogeneous. Next, I'm going to draw some of that solution into a barrel pipette to make the transfer a little bit easier. And I'm going to transfer that reaction mixture into an empty cuvette. And I'm going to place a lid onto that cuvette. And I'm going to put the cuvette down into the cuvette slot. We're now going to begin data collection. I'm tapping on the collect button, and we go to a graph of absorbance versus time. You can see the data is now being plotted on the graph axes. Absorbance value is decreasing against time. So now we're nearing the end of data collection, nearing the 200 seconds, and you can see at this point that the concentration, the absorbance value has dropped to nearly 0. The graph is auto-scaled, and so at this point we're going to do some further analysis. This is the type of thing the student would do for this particular experiment. Notice that we have absorbance plotted on the y-axis. The method we're going to use for the analysis assumes that absorbance is proportional to concentration, which is just Beer's law. And so you can think of the absorbance as being a concentration value. And so we're looking at concentration versus time. So if this graph was linear, that would indicate that the reaction is 0 order with respect to the crystal violet reactant. It's clearly not linear, but just for comparison purposes, we could put a linear regression on here. So I'm going to tap on the Analyze menu, and I'm going to go to Curve Fit, and I'm going to do a curve fit on absorbance. And on the curve fit screen, I'm going to choose a linear fit. And we'll just find out how linear it is. And notice that it gives us a linear fit, y equals mx plus b. And the correlation coefficient is minus 0.9777. So it's not really all that linear. Our eyes told us that, but now the statistics tell us the same thing. And we're going to be comparing these correlation coefficients, so I want to know what that is. To remove that correlation coefficient, I'm going to tap on Analyze again, choose Curve Fit again, and tap on the checkbox, and that takes that away. Now, in this method of analysis, we also want to see if it's a first-order reaction or a second-order reaction. To do that, we need to create 2 calculated columns, one for the natural log of absorbance, which is going to tell us if the reaction is first order with respect to crystal violet. The second one is the reciprocal of absorbance, which is going to tell us if it's a second order reaction with respect to crystal violet. To create a calculated column, we're going to tap on the table screen, tab, and on the table menu is where we actually, because this is where we deal with data, this is where we're going to create those 2 calculated columns. So we're going to tap on New Calculated Column. The first column I'm going to create, I'm going to highlight calculated column, and I'm going to rename that LN for natural log. And then I'm going to put in absorbance, A, B, S. I'll just abbreviate it. And then down here where we select the equation for that column, I'm going to pull down that menu. And I'm going to scroll down to natural log, A times natural log of X, and I'm going to choose that. And if I scroll down a little bit further there, I'm going to use, for the column for X, I'm going to use absorbance, and I'm going to use a value of 1 for A, for that constant, and I'm going to tap on OK. It actually plotted that for me, and so now I can see the natural log of absorbance versus time. That looks like more of a linear plot. If that's the case, then that means that this would be my first order reaction. But let's find out what it is and not jump to conclusions. So we're going to go curve fit again, natural log of absorbance. And I'm going to choose the fit. I'm going to choose linear. Again, I get the statistics here. And the most important one is the correlation coefficient, which this time is 0.99985 or 0.999. So that's a nice correlation for a linear fit. We have a few points off there, but not far off. And that would suggest to us that this reaction is first order with respect to crystal violet solution. Finally, the third graph that we look at in this process is going to be the reciprocal to see if it's second order. So let's choose Analyze, and let's get rid of that curve fit. So now what we want to do in order to do further analysis to see if it's a second order reaction, first we have to go and create that calculated column for reciprocal of absorbance. We're going to return to the table screen. We're going to choose Table. We're going to choose New Calculated Column again, but this time we're going to create a column that we'll call Reciprocal Absorbance. I'll use ABS again. Now I'm going to choose my equation, and I'm going to choose the reciprocal, which is A divided by X. And I'm going to scroll down here a little bit, and A is 1, and the column for X is absorbance at 585. I like that, so I'm going to choose OK. Just visually, it doesn't look very linear, and just for comparison purposes, we'll put the linear fit onto this one, and we'll choose for a curve fit linear. And the correlation coefficient comes out to be a much weaker 0.987, and so we can, by comparing those three correlation coefficients, the 0.987 and the 0.977 we'd reject, and the 0.999 value for the natural log of absorbance we like very well. So it looks like it's clearly a first order reaction with respect to crystal violet. And for my final lab report then, I might go back if I was a student, and I might choose again to go back to natural log of absorbance versus time. There's that very pleasing linear fit. This is an experiment I used in my own teaching. My students always enjoyed doing this experiment because they had some nice visual feedback of what was taking place color-wise by watching the fading of the crystal violet color and then using an instrument to monitor that same change and get back some nice numbers. The analysis is certainly very nice as well, that you can follow up that reaction and see those graphs just like you'd see them in your textbook, only you created those graphs yourself. Finally, the fact that this reaction just takes place in just a little bit over 3 minutes makes it a delightfully easy lab to complete in a lab period. It's a great lab for an AP high school class. It's a great lab for a general college chemistry class. It can even be simplified and used in a first-year chemistry class.